Okay. Well, welcome everybody back to the now our second lecture in the May workshop of the Simon's collaboration on special holonomy and geometry and analysis and physics, geometry analysis and physics. And it's a pleasure to welcome Mike Douglas from Harvard and CMSA, who is going to be speaking on numerical Calabi-Yau metrics from holomorphic networks. Michael?
Yes, thanks, Robert. Thanks, everyone, for the invitation. So I'm going to be talking about joint work with students from Stony Brook, Yidichi and Subramania and Lakshman Narasimhan, and a third student, Tudor Chobanu, who began the project with us, but tragically died before its completion. So this is work in one of the papers in his memory. And there's a second paper which I put out very recently, which is a more mathematically oriented summary of parts of the work. So okay, so we have this problem of Kähler-Einstein metrics, which is better understood theoretically. But of course, theoretical methods still have their limitations, especially if one wants either details of complicated solutions or simple numerical results. So in physics, we like to know normalizations of eigenfunctions of the Laplacian or Dirac operator and products of those Yukawa couplings. So those motivations have led there to be a steady stream of works on this numerical subject since it was initiated by Hedrick and Wiseman back in 2005. And of course, Simon reviewed a main stream of that work, which he introduced, which uses an embedding method, which I'll skip over. I have review in the slides, but I'll go through it very quickly since Simon did a lot of that. And then the point that has brought me and a number of us back into it, of course, is the tremendous progress in machine learning, which is relevant to this in various ways. And the one which I'll focus on in this talk is to use feed-forward networks, which I'll explain, to represent the Kähler potential, the functions which are involved in our problem. And then this is a very active subject in applied math, in particular, using these methods to solve various PDEs numerically. Of course, Navier-Stokes equation, the many-body Schrödinger equation, that sort of thing. And I won't be able to do justice, but there's a fair amount of work. I will at least mention some of the main questions that people are studying. And then the second relevance is that because machine learning is such a useful and intensively studied subject, the software and the hardware to treat it is far more efficient than a general purpose numerical code. These packages like TensorFlow, which if you can modify your problem in some way, fit it into the specific kind of framework that these machine learning tools can handle, you immediately have the power of a supercomputer, more or less, on your laptop. And so it turns out that the approach that, in fact, our work, following Donaldson, the particular variations that we had made in my work with Karp, Lukács, and Reinbacher fit directly into a machine learning framework, as you'll see. And so we were able, with really relatively little programming effort, to get quite powerful code. Okay, so here is mentioning a few of the works of others on the same subject, and they'll speak, of course, at this meeting. So, excuse me. Okay, so again, just to review notations as much as anything else. The examples that I'll talk about are all quintics in CP4, so these Calabi-Yau threefolds. And then what will come out later is that compared to the previous work, the big advantage of what we're doing is that you don't need to assume any symmetries of the quintic. And so I've only written out this standard kind of dwarf family, but in principle, of course, you could write a general polynomial and access the whole 101 parameter moduli space. And, again, as in Simon's talk, there's a simple reformulation of the Ricci-flatness condition in terms of equating the Kähler volume form with this volume form constructed from the holomorphic N form. And so that is a simplification. And so then, well, again, out of the various, many ways you could try to do a numerical solution, the first distinction is a local method where you represent functions, roughly in terms of their values in, a point or some small region or neighborhood. And then, obviously a vast area, the most sophisticated methods tend to go under the name of finite elements. And there's been a fair amount of work on finite elements for geometry, finite elements, even to formulate, Einstein's equations. There are papers, for example, of, Yau and collaborators over the years here. And then the other big branch is what tends to be called spectral methods in the numerical literature. And the basic example would be to go to a Fourier space, but more or less anything where you have non-local spread out basis functions that are defined by some sort of spectral or differential condition. Okay, so those are, again, just to situate us in this big landscape. Another issue which has been very central, in particular in the numerical relativity, which is done in physics, are the need to deal with the coordinate general covariance, the fact that there's no a priori given coordinate system in general relativity, and certainly for our geometric problems. And then this almost always leads to problems that you generate coordinate singularities if you're not very careful on how you treat this. And then the breakthroughs in numerical relativity over the years tended to be treating this issue. So here, that's an advantage of the Calabi-Yau metric, is that to a large extent, the procedure that we'll talk about mitigates this, but this would certainly be an issue for talking about general Riemannian geometries as well. Okay, so now let me just very briefly, review this train of work. So there was this pioneering paper of Hetrick and Wiseman, which was more motivated by this numerical relativity literature, and they used a local, a sort of a finite element approach for the Kummer surface, and they split it into the orbifold and patching in these deformed Iguchi-Hansen spaces, and then represented the Kähler potential in terms of its values on points. And then, in general, these, elliptic equations, and you can use relaxation methods. You just locally average, do some appropriate average to determine the value at a point in terms of the values at neighbors. And that tends to work well for elliptic problems. Okay, so now you see here what, from a numerical point of view, people would consider to be the main issue in all of this. I guess everything else is kind of well understood. And what's also well understood is this thing called the Curse of Dimensionality, which is to say that if you imagine some sort of a lattice, then of course so points in your manifold, then the spacing between the points directly controls the smallest length scale on which you can represent variation of your geometry or your functions. And then in dimension D, you're going to go as that length in lattice units k raised to the D power number of finite variables that you need to represent your functions. And then, even on a supercomputer, unless, unless you're doing something like, 3D weather simulations where you can really afford a vast supercomputer, even a billion points would be a very, very big problem. And then for D equals 4, that's telling you could get maybe 100, which is respectable. But for D equals 6 already, you can't get this K to be very big. And now, we're talking about huge numbers of points. And so this power-like growth is what people refer to as the curse of dimensionality. And of course, in physics and quantum physics and game theory, in many problems, you get dimensions, hundreds, thousands, and then of course this approach is useless. And here we're in sort of this borderline situation where for dimension 6, we can certainly think about k to the 6, but if you went to talk to applied mathematicians, they would say already Navier-Stokes in 3 dimensions. This is a problem. 6 is really going to be hard. Okay, so but that's the nature of the problem. And then the other issue that one would generally have in our application, of course, is that our manifolds have complicated topology, then complicated structure. If you try to represent functions in terms of the values in the coordinate patches, well, of course you can do it. We know how to do it, but it's a fair amount of work then to program that all into the computer, and people are not going to give us a lot of help. As I say, the machine learning problem, we got a lot of very eager computer scientists solving those problems for us, but describing the topology of a generic high dimensional manifold, we are not going to find so many computer scientists that are willing to put a lot of time into this. So it's not that it's a problem in principle, but certainly in practice, it produces a lot of work. Okay, so that's the Hedrick and Wiseman, the sort of issues that you would face in continuing that direction. Okay, so then Simon's work was inspired by, but what really quite different. And again, just to set it into this larger context, this is what people would generally call a spectral method. And of course, what we're doing is we're embedding the manifold by the sections of some line bundle. And then that's a simple differential condition, of course, that we have a holomorphic sections. And the thing which is this is kind of analogous to in the larger field of PDE is that people do try to embed things by eigenfunctions of a Laplacian. That's actually a very popular technique in machine learning. And that, of course, you don't need to have a manifold. You can talk about graphs or anything where you can define a Laplacian. And so there are already interesting points of contact there. And the general idea that on a complex manifold, you don't even have to have a Laplacian. You can have these simpler structures that give you this preferred embeddings. Seems like one that they have not really pursued very much in terms of graphs or other structures and embeddings. So that's an interesting question to think about. But we'll grant that we have some preferred embedding. Then the idea is that we use it to embed into a simple space that we can put into a family of Euclidean metrics on, and then we pull those back, and we get a family of metrics that we can use as a variational space to find the best solution of our problem. And again, one has the problem that if the embedding has nothing to do with your problem, then it's quite likely that there'll be many kind of bad and singular limits in this embedding space that will, again, hurt you in terms of, doing real algorithms. But here, the embedding is nice for this problem. And again, that was implicit or even explicit in Simon's talk that basically, as we'll see, the optimization function on metrics with embedding by sections of line models is a nice problem. Okay, so the again, the kind of how to say naive approach to this would be to say, well, let's first take the original embedding. We defined the thing as a hypersurface in CP4 that embeds it into a CP4, but that gives us a very small dimensional parameterized space of metrics. But to do better and get larger dimensional parameter spaces, we can take higher degree bundles, and then and it's a concrete case, just take a homogeneous polynomials of some higher degree. And so that's a general and even canonical set of embeddings, which, again, for these Kähler-Einstein problems, and are, I would say, less likely to introduce bad behavior. We'll still see potential bad behaviors, but at least we can understand it. Okay. So then the another ingredient, of course, that Donaldson introduced and he spoke about is the idea of the balanced metric, which I don't need to repeat. It has interesting physical resonance. You can think of it as the condition that the density of states for some system where you populate the various, so in the physical translation of these holomorphic accessions, one of them is that you say these are lowest Landau levels of a quantum Hall system where the magnetic field is the Kähler form. And so then this is a condition that the density of states of that system is constant. And, it's an interesting contact with physics with that. Okay, and then of course the interesting point for the Kähler-Einstein application is this fact that given suitable conditions, then as the degree becomes large, the balance metrics converge to a Ricci-flat or a Kähler-Einstein or constant scalar curvature metrics. And out of the various definitions, almost always, for most purposes, and certainly for numerical purposes, one would be happiest with a definition of your problem that extremizes a action or an energy functional. And so one also could have that for the balance metrics, this type of convex functional. Okay, and then of course there's the iterative scheme that Simon described in his talk as well. And then a number of physics works followed up and used that. So we introduced this kind of Monte Carlo approach where you don't need to, all you need to do is program a way of sampling points on the manifold, which in the case of a hypersurface is quite easy and generally is easy. And then you do integrals by Monte Carlo, and you don't need to represent the manifold in terms of patches or anything else. And there's generalizations. I'll talk a bit about this later, the Hermitian-Yang-Mills equation, more general toric, hypersurface and toric varieties. And here's an example from our original 2006 paper of this ratio eta of the two volume forms restricted to a S2 in the Fermat-Quintic. And you see as K increases, it gets better and better. The Ricci-flat metric would be a perfectly round sphere. The radius of these things is this ratio eta, but you can still, even for K equals 12, by eye, see the difference between this thing and the round sphere. And that's saying that it's converging, but it's not converging very quickly. And so then you could say, well, if I'm really interested in the Ricci-flat metric, why am I looking at the balance metric? Why don't I just look at a energy functional that is minimized for the Ricci-flat metric? And that's what Hedrick and Nassar did in their work. And of course, you could just take norm of eta minus 1 as such a thing. And there are various interesting choices here. One that comes up a lot in machine learning is what's called the Kullback-Leibler divergence. That is to say, you take the two volume forms and interpret them as probability distributions, and then there's the natural distance between them as probability distributions. But it really doesn't matter which one you take. They're all convex. They're all very good functionals to try to minimize, as long as you either do the continuum integral or do Monte Carlo with a large number of sample points. And I'll come back to that issue. And so then Hedrick and Nassar looked at, again, these Fermat, Dwork, K3, and Quintics. And then the thing which allowed them to follow this very simple procedure, and true for really almost all of this previous work, is that we are taking manifolds with a very large discrete symmetry group. And so you can much reduce the number of parameters. Of course, ultimately, the asymptotic growth as a power of K is the same, but the low order number of coefficients is very small. Even they got up to K equals 17 on K3, and there's still only about 100 coefficients. So this symmetry group really helps you. Okay, so there is this choice, and the thing I've been saying in my talk, and everybody can weigh in on this, is that clearly the balance metrics have great mathematical advantages, and if you either want to rigorous proof of something, or you don't know whether the solution exists and you want to somehow study the question of whether the solution exists, probably it's better to do that with the balance metric. But if you know the solution exists, you really want the most accurate approximation to the, say, Ricci-flat metric, then you should optimize that error. Okay. So now, again, repeating comments that Simon explained, that as a Fourier space or a spectral approximation to a smooth metric. In this case, the approximation error decreases exponentially in the order k. And then one also has this general property that the degree of the base is going to control the structure, the length scale in which you can reproduce structure. And then as Simon mentioned as well, of course, we have a moduli space. We can easily take limits where in the limit we would blow down some cycle, say in the physics literature, get a conifold singularity and get the curvature to become arbitrarily large. And then this fixed k would be problematic. You would want to use a larger k to represent the large, the faster variation of the function near this singular point. And then now you have this curse of dimensionality. If you try to increase k every place, you get this k to the 6 number of coefficients, all of which will have to be stored in the computer. And again, you can sort of do it, but it's this becomes the limiting factor. So both problems where you don't have the symmetry and problems where you have some singular, you're approaching some singular limit that produces structure on multiple scales. And so then that's the kind of issue that the methods I'll talk about can deal with. Okay, so then Ashmore, Hay, and Ulbrich were really the first to bring in some of these machine learning techniques, and I refer you to their work, and it would be interesting to again see the value of their techniques for manifolds with less symmetry. Okay, so this curse of dimensionality is not just a classic issue in numerical computation, but it's the fundamental problem of machine learning, that we're trying to do things like recognize whether an image is a cat or a dog, and the image has millions of pixels. So just the whole definition of the problem involves these very high dimensional spaces. And so conversely, once you see that you have new techniques for dealing with functions in very high dimensional spaces, then maybe those techniques can be used to solve PDEs numerically in better ways. So I've given a couple of references. Okay, so now we'll get to the heart of the talk and the definitions and the system that we implemented. And our idea is to define a feed-forward network, which represents the Kähler potential for the manifold of interest. And so what is a feed-forward network? Well, many of you have probably seen this in discussions of machine learning, but what it is for us, so we've got some input vector space, which I've called calligraphic X here. And we have some output vector space Y. And here, X might be the linear space into which we embed our manifold, and Y might just be the one real dimension, the value of the Kähler potential. And so now we're going to define a parameterized family of maps from X to Y, and then we're going to solve our problem basically by optimizing some energy functional of this map F with respect to the W's. Okay, so the kind of maps we're going to talk about are an alternation of two types of maps, and one is just a linear map, but it doesn't have to preserve dimension. It can go from, the first one will go from X into some new vector space V1, and then we have some nonlinear function, which I'll describe shortly, called theta, that takes you from V1 to V1, some nonlinear transformation. Then we've got another linear one, W2, that takes V1 to V2. And then we just keep doing this. We have W theta, and then we end up with a W. And so then theta composed W is generally called a layer, except for this last guy that doesn't have a theta. So the simplest thing like this you could do would be a depth 2 network, W composed theta composed W, but you can go to arbitrary depth. And that's a feed-forward network. And the parameters are the choices of these maps W. So it's just very explicit, but it has this interesting nonlinearity in the definition. Okay, so what is theta? Okay, so I explained, we have some field in which, our vectors are defined, K. We have linear transformations, W. Theta is called the activation function. And basically what you're going to do is pick some function and then pick a basis and just apply the function component-wise in that basis. And of course, in general, that would depend on the choice of basis. But since we're only using theta in between these general linear transformations, of course, the space of maps you get doesn't depend on the choice of basis. We've entirely removed that dependence by allowing these arbitrary variations of the map W. So now we ask what kind of function do we need? And then the general claim that it doesn't matter that much. And in fact, the one that gets used by far the most in the practical applications is something that they call ReLU, because it comes out of engineering, rectified linear unit. And it's just to say function of x is x for positive x and 0 for negative x. And so that's nonlinear and extremely easy to implement on a computer. It does not require any non-trivial operations except just this one conditional operation of testing whether the number is positive. And then one which was motivated by physics and information theory is a tanh x, and then there are many others you could take, but this ReLU is what you usually see in practice. Okay, so that's it. That's the whole big class of feed-forward networks. And then this is really the kind of the mathematical definition at the heart of these, like if you see a program that recognizes that this thing is a cat and this picture is a dog, or all this kind of stuff, it's this and at the heart of it. Okay. So mathematically, people have studied the ability of these things to approximate functions quite a lot. And even with 2 layers, you can approximate arbitrary functions, but you tend to need an exponentially large number of units to do it. And as you increase the depth, as you go to, like even depth 3, W theta, W, you can show that it's easy to make functions which a 2-layer network would require an exponential. By units, I basically mean the dimension of these intermediate spaces. I should stress that we chose, these would be like, k to the d1, k to the d2, and we choose those numbers. And, from some computational point of view, it's better if you can get away with smaller numbers, but, it's quite fine if they are thousands, tens of thousands, not billions, but, tens of thousands is okay. And so as long as you're not growing exponentially, you're in good shape. And so even as I was mentioning, so it's easy to come up with functions where a 3-layer network, you do not need an exponentially large number, but you would have for a 2-layer network. And this is considered a very interesting, and it is a very interesting question. What can you approximate? What is the function space that you describe with a given class of networks and a given number of layers? And here are some of the, again, to my eyes, more mathematically interesting and penetrating papers on these questions and their application. Not for machine learning per se, which of course there's quite a few papers, but specifically for solving partial differential equations. So Wayne Ani and Stefan Vojdovich, for example, this is a good reference. Okay, so that's the general framework, and now we're going to represent the Kähler potential of our Calabi-Yau metric by this type of construction. And the basic motivation working is very simple, that the concrete description of these sections for a hypersurface in a projective space is just going to be homogeneous polynomials in the coordinates on the projective space. And so rather than list all the homogeneous polynomials to some degree, we're going to try to produce a feed-forward network of this type, which produces homogeneous polynomials of some given fixed degree. And since W is linear, the obvious other thing that we can vary to get homogeneous polynomials is this function theta. And if it's going to be homogeneous, then theta has to be homogeneous. So let's take theta of z to be z squared. Okay, so that holomorphic function. And so both of these things are holomorphic. So this whole transformation is holomorphic. And as I mentioned, we apply this z goes to z squared component-wise, but that did not add any additional choices into the problem. And so that's what we call a holomorphic network, this composition of linear maps with the nonlinear function z goes to z squared applied component-wise. And so then we can use that to produce a Kähler potential by replacing the sum over the complete basis of sections of some degree with the output of one of these networks, which if we have L layers, we're going to get, if we take the inputs to be just the coordinates of degree 1, we're going to double the degree for each theta. So we're going to get degree k to the equals 2 to the L minus 1. Okay, but it's going to be some chosen dimension. So it's going to be obviously a subspace, and for unless this dimension is very large, it's going to be a subspace of all the sections. But we could take that subspace, and then we could just take log of sums of squares of that, or again, it would be redundant to specify the metric at this point, given that we varied these WDs. But in any case, that would be a style of network, which we'll call holomorphic network, that produces a subspace of the space of sections of LK, where the subspace is parameterized in this interesting, non-trivial, but not incredibly complicated, but non-trivial, nonlinear way. Okay, so then another option which we found works better for this problem is to not take a holomorphic network, but to take the degree 1-1 sesquilinear combinations. So let's say the real and imaginary parts of all the ZZ bars, where these are the projective coordinates. And so then we feed that in, and that's bihomogeneous of, we'll say, degree 1-1. And then taking the same theta goes, z goes to z squared, we again double the degree at each stage. So we get out something which is bihomogeneous under rescaling z and z bar of degree 2 to the L, 2 to the L. And then that guy is directly available. We just can take log of a one-dimensional output to get a Kähler potential. And so that's a bihomogeneous network. And for this case, the inner workings, all the coefficients in these matrices and the intermediate results are real numbers. Okay. So it turned out we tried both of these things, and the holomorphic networks don't work that well. And leaving out I won't say that much about it. I'll just say that even writing down a non-degenerate Fubini-Studi metric at high degree, of course, you need to have all the sections, and then taking a lower dimensional subspace of the sections gives you this degenerate Fubini-Studi metric, which seems to show up in degeneracies after you restrict to the Calabi-Yau, or the manifold of interest. So that showed up in poor behavior of the programs in various ways, but these bihomogeneous networks do work quite well to represent the Kähler potentials of Ricci-flat metrics. And so, it's easy to see that they fixed the problem we just said, that once you feed in ZZ bar, it's easy to make the it's of course you immediately get as the output of the first layer the degree 1 Fubini-Studi e to the Kähler potential, and then you can just keep squaring that thing and keep having a single dimension 1 all through, and you'll just multiply that Kähler potential by whatever factor you need to get a Kähler potential coming from a higher with a higher class. So it's clear that you can represent at least the simple Fubini-Studi metrics, that and in particular that if you have a metric that you get from a network of depth d that simply embeds in the metrics you can get at depth d+1. So you can take a solution to the problem in particular, and then add another layer, and then start adding additional terms to modify the metric, and then you perhaps make it a better approximation. In particular, you can add terms that are sharply peaked at points of the Calabi-Yau manifold, and so that's in principle argument that yes, we are given an approximation at some degree k, you could add another layer and do better at layer 2k. So obviously very heuristic argument, but very plausible at that point. And again, just for explicitness, if it helps in thinking about these definitions, these would be bihomogeneous networks of depth 2 and 3. And here I've taken the inputs to be sections S. They don't, of course, have to be the homogeneous coordinates. They could have been some higher degree list of sections. So we're going to feed in these combinations, SS bar. We're going to take a set of linear combinations of those indexed by this explicit capital I, and then we're going to square those. That's the theta, and then we're going to add those up. And finally log to get a Kähler potential. And then here's adding a third layer onto this. We do what we did before, and then we square it again and add those up. And so then this will be the dimension of the space of parameters. And it does not grow as k to a power. So I recall that this complete set of basis functions and so complete space of Fubini's 2D metrics grew as power k to the real dimension, so k to the 6. But if we keep the intermediate dimensions, the widths fixed, then, or even if we let them grow, as say with the depth of the metrics, nevertheless, the depth is a log of the degree, and so this is basically growing. If you call the other growth exponential k to the 6, then this is growing logarithmically. It's growing much less quickly, but you can still represent structure on scales 1 over k, as I described. Okay, so that's the setup, and that's the new mathematical ingredient, and now we just more or less, it takes a little programming, but to a good extent, you can just plug this into a TensorFlow. And so we're going to take an error function, which is this word that Hedrick and Nassar, and of course, it's many other people use, that we have a let's say least squares error, and now the essential point at which this problem is like supervised learning is that both what we're doing and supervised learning are problems of function interpolation. Okay, so function interpolation, we're given a set of pairs, xi, yi, so input, comma, output, and we have sampled from our space in some way, and now we want a function that tries to minimize the error over the defined on the whole space, right? So we basically have to assume our function has come out of, in the machine learning application, you would assume your function came out of some sort of statistical ensemble of images or whatever the thing is learning, and now you want to maximize or minimize the expected value of the error of the function, given that you've fit the function at some finite list of points x and y. Okay, so that's a basic problem of numerics and machine learning and so forth. And now let's look at our Calabi-Yau problem. Well, our Calabi-Yau problem was the special case where we're setting two volume forms equal, the Kähler form and this holomorphic volume form. And the holomorphic form is something you could just write down and compute at a point. The Kähler form depends on the particular Kähler potential, which depended on these weights W. But once you know the weights W, you can just compute this. And if you have an expression that you can take derivatives of, you can just compute that volume form as well. So basically what you do is you sample from the manifold, the Calabi-Yau, you get some sample of points X according to some volume form. It could be the holomorphic volume form. It doesn't even matter that much. And then you compute Y. Okay, you compute the holomorphic volume form at that point, and now the function interpolation problem is given an input ZZ bar for a point, predict this output, the value, you normalize perhaps against the Fubini's 2D volume form, but the value of this holomorphic volume form, and then this Kähler function is the space of functions that we're using to solve the interpolation problem. We're trying to find the best interpolating function within this approximating space. And so all those ingredients are standard numerical machine learning agreements with this one exception. Even taking these derivatives is a standard thing. This is what they call backpropagation. The only thing which is really a little bit more work is take the determinant of this at the end to get the volume form, but that's very easy. So it was actually pretty easy. And of course, I had a very talented student, Yidichi, who was quite expert in making TensorFlow do what he wanted. But the basic nature of the problem that we set up was that this was not so hard. And so here is how an example of one of these networks would be programmed in TensorFlow once you have the layer. So if you're familiar at all with TensorFlow, in fact, these are the standard things. So in fact, this square activation function, z goes to z squared, is a standard thing in TensorFlow, although people don't use it very much. But it was there for us. And then these are these layers where you have, so dense just means there's no restriction on the linear transformation that you allow in that layer. We put in this bihomogeneous function to generate these combinations, ZZ bar, and then there's a determinant function somewhere in here. And so both the calculation required to compute the error function that we minimize and the minimization procedure and all the other programming stuff that you need to keep track of the results and save your coefficients and test your errors and so forth was all already there in TensorFlow. Okay, so that's okay. I don't want to spend a lot of time on kind of technical details of the thing. I'm just going to briefly point through some of these things in the slides, which you can look at later at your leisure. So these are a few numerical details. There's this question about whether the loss function is convex, which is always very central. And although this is a nice problem where if you really take the functionals on the whole space of Kähler metrics, they would be convex. Here, there are other issues, and one of the big issues is that we typically don't have enough points. Okay, if you think about it, there's this question of can you interpolate every function? Okay, so if you have a number of points, you're given a number of samples, xi, yi, and you have a number of parameters, and if you have a lot of parameters, then you can interpolate every single set of NP, for a given NP. If the number of parameters is much larger than NP, you can interpolate every possible function. And then that's what in statistics people would call the overparameterized or the overfit regime, where very typically you have models that overfit and see noise in this thing, and it's problematic. And it's less problematic in machine learning in general. It's less problematic here, but it does lead to this loss of convexity is one place where the difficulties show up. Okay, so what do we do in terms of actual tests of this framework? So as I mentioned, the big advantage compared to the previous techniques is that we didn't have to make any symmetry assumption. And as such, we're going to get very large numbers of coefficients, but we're using this very powerful TensorFlow GPU setup where we can deal with models with millions of coefficients. So that's not a problem. And so we, of course, did start with the Dwork family, but then we postulated two more families, which have less symmetry and no symmetry, and wandered around in the space of the two-parameter moduli space to see how the error depended on the parameters and see what we could learn. Okay, these are again general comments about optimizing the various choices that you make in the procedure. This is how the error behaves as a function of gradient descent steps. So we're using the standard kind of gradient descent from most of the training. And this is a very typical looking kind of graph in machine learning. And then eventually what we focused on was we'd like to understand the dependence on these what properties of the Calabi-Yau. This question of whether it has symmetry or lack of symmetry, okay, is one question. So that we've scanned through three choices here. And then this question of how close you are to a singular Calabi-Yau, or what's the shortest length scale, what's the scale of variation of the functions involved. And then a basic question that you could ask about that is, well, how many parameters do you need for a given error? And in particular, what controls the number of parameters you need? Is it either of these factors? Is it both of these parameters? Is it, and so we needed to measure, we needed to quantify. We didn't quantify this lack of symmetry more than we did, but we did quantify the shortest length scale on which there is a structure. And we did that, again, I'll just mention this in passing. You could compute in the moduli space, basically the shortest distance to how to say. So we've embedded this hypersurface, and then there would be a distance to the discriminant locus in the moduli space. And rather than a proper definition of this distance would use a Hodge theory and measure it in terms of periods, but we took a sort of simplistic version of that using Fubini-Studi distance in the space, in the moduli space. But again, as you approach a singularity, this is probably a reasonable thing to do. And this is an example for the Dwarf clinic as you vary psi along the real axis. So here's the conical point. Here is another minimum of this proxy or measure of how close you are to the singularity, showing that there is a second minimum, which was observed in the work of Qui and Gray, that errors in these metrics also have a shape like this. Okay, so this is our two non-trivial Calabi-Yau families, and these heat maps saying that down in this red part, you're far from the discriminant locus and presumably far from any conifold or singularity, and blue is getting close to the conifold locus. And you can see that the structure is quite complicated, especially for this F2 family with no symmetry. And then the kind of data we got, we did a lot of runs varying the moduli and considering networks of various types. So 2, 3, 4, these colors on the right are telling for these top series of dots, considering the general Fubini-Studi metric with k equals 2, 3, 4, and then we're comparing it with a 3-layer network with width 50, that's 50, 51, a 4-layer network with 70, So 4-layer now getting us, I guess, k equals 8. And then with 300, and then there are these various series of colored dots in this graph. And then finally, the bottom dots here, S8, are what you get if you grant that errors will decay. For the optimum, the error will decay exponentially in the degree k, and you fit an exponential to the result you get for these 2, 3, 4. So the Fubini-Studi already for degree 8 with no symmetry is a little too big to do easily, but this extrapolation seems to be good. And so for this F1 manifold with some but not much symmetry, you can see that this best network with 300 can get as good results. So that's k equals 8, but it's getting as good as the general k equals 8 metric would be predicted to be. And then here is the F2 case. And now this is showing that, again, we've got some best possible error. It gets better as you get away from the discriminant locus. And if you take the 300 width network, you can match that best possible area. But already when you go down to the 70 width network, for the, except in this kind of far from the singularity, you get a measurably worse error from this width 70. So that's an example of the type of behavior that we found. And so what do we learn from that? Okay, and so the basic thing we learn is that, well, clearly this degree, this question of what color dot we have here is a big effect, but the width is also a significant effect. And you can see if you look at the details, the amount of symmetry is at least a measurable effect. And so the question is the error more determined by this k, the total degree, or is it determined by the number of parameters? That's the question that emerges from thinking about this data. Okay, so if you compare the number of parameters now for the general Fubini-Studi metric of k equals 8, it's 245,000 or so. This 300 width network that was able to match it has fewer, but not that many fewer. It has a very comparable number of parameters. This 70 width network had only about 11,000 parameters, so sizably less. And then here you see, well, for some of these, if you're far enough from the discriminant locus, it seems like the width 70 network with many fewer parameters can describe even this Calabi-Yau, this particular Calabi-Yau with little symmetry. But as you move closer to the discriminant locus, you see a distinction where you really do need more parameters. Okay, and again, I think one could do quite a bit better. This was exploratory, but in terms of understanding what were the issues that one would like to understand, and this question of what governs the ability of the network to approximate. And so, anyways, we did publish our code, and we have, I would say, a pretty solid system to do calculations for these k=8 metrics on Calabi-Yaus. We've looked a bit at the problem of finding SYZ fibrations, but I don't have results to report. And to try to ask some sort of a crisp, more as much computer science as mathematical question, we can ask this question of, given a series of networks where, as I mentioned, the general metric would have the number of coefficients grow as k to the real dimension of the manifold. Now, suppose we insist that the number of coefficients grow as a power of log k, so the power of the depth, so growing much less quickly than this. Are there functions that cannot be well approximated by such a restricted network? So clearly this is the best you could do. And it's you could ask the same question about polynomial approximation. It would be more sophisticated to measure geometric quantities, but the basic question here would be one of polynomial approximation. And my belief, not having any very convincing argument, my belief at this point is that definitely there are functions that do require all the coefficients. And so the neural network of a given fixed width, even for arbitrary depth, does not have the approximating power in general of the general function. There are functions that you could not well approximate that way. And the second reference I gave, the single author paper gives some heuristic arguments to that effect. I don't want to try to go through it in detail, but again, some reasons to think that. Now, that would be a worst case result, and it's possible that the Ricci-flat or the balance metrics are better than that, and that even if you can't approximate the general function or even the general smooth function, maybe you can approximate the general Ricci-flat metric that way. So that's an interesting question, which I think one would, the preferred way to think about that would be to adapt this construction of balance metric in some way to the networks that I'm talking about. So that's another interesting open question. Okay, here I'm saying a little bit more about this question of overparameterization, which is quite interesting from the machine learning point of view, but I don't think I have time to do justice to it here. And then, okay, I'll skip that. Let me just mention a couple of variations on this, which I think are worth pursuing. And I talked about a network which had a sort of linear structure with layers and an activation function z goes to z squared. But if you think about it, then that's just a special case of what's really a tree structured network, where instead of taking z squared, you have distinct z1, z2 inputs, and you take the product z1, z2. And so in this geometric application, we were parameterizing holomorphic sections of, say, degree K1 bundle, degree K2 bundle, then we multiply them and we get a section of K1 plus K2. And we can think of that as defining another class of network where we sent two inputs into this operation and got one output out. And so we can get a sort of a tree structured graph. And so that's an evident generalization. But once you see that you can produce networks with other types of graphs, you can do much more different things. And another type of construction which has been used quite a bit, for example, in quantum many-body physics, is what's called the matrix product state. So here, I'll just describe it in our application. We're going to take the parameters to be a tensor, which is a linear map from a space of linear maps of an auxiliary space, LL, into the space of interest. And so here we're going to take the parameters to be this tensor T, and we're going to take a, so in physics terms, a three index tensor, or coordinate valued matrix. Okay, so a matrix whose entries are first degree polynomials, and then we'll take trace of T dot Z, T dot Z dagger, T dot Z, T dot D Z dagger up to some given degree D. And that's an equally natural and different approximation scheme, which is much like these matrix product states. So that would be an interesting thing to explore. Okay, here's a few notes on how you would adapt the same strategy to do Hermitian Yang-Mills. And I think the interesting point here, obvious but worth saying, is that there's no direct analog of this Z goes to Z squared map. So you can start out the same way. You can say, we're trying to, we have an embedding of some twist of a vector bundle E by L to the K, which embeds the manifold into some Grassmannian by its holomorphic sections. And then we take a sesquilinear sum of these sections to get not a function on the manifold, but this matrix, which we're going to use to derive the vector potential. So this Hermitian-Einstein, we're trying to look for a Hermitian-Einstein metric, so-called. And so all the setup starts out very similarly, but then you get to the point of defining this theta operation. And I don't think it really makes sense to square these operations. They are matrices. In principle, you could do something, but I don't think that makes sense. But what would clearly make sense would be to take the product of one of these matrix things with the function produced as sesquilinear combinations of the coordinates or higher degree sections of line bundle. And so here would be an example of a second network which uses as inputs pieces of a first of the network we were previously describing. So this type of WZZ thing, or perhaps more layers where you square this, and then having a second network where you feed in these sections, linear combinations of sesquilinear combinations of these sections, and then rather than try to square this to basic operations, to multiply one of these by one of these function approximations coming out of a neural network, and then you could have a series of these operations, if you like. And so that would be the natural version of these networks appropriate for Hermitian Yang-Mills, which in some sense is like a module on which the original network outputs act. Okay, so that's what I wanted to say. And so we have a package which one can, again, there's a lot of generalizations which would require programming, but straightforward programming. And I think this level of 0.1% accuracy and some generality should be achievable with, again, not a big computer, just any kind of good sized computer with a GPU. I used my own. We used a variety of GPUs for our calculations. They don't have to be, industrial strength ones. I talk about a few theoretical questions which do make contact with theoretical questions of interest in the machine learning literature. Again, you can see the paper for quite a bit more detail about that. One thing I thought I would mention at the end, which is very tangential, but I find very intriguing, especially if any connection could be made, is that in the recent years, Avi Vigdorson, a computer scientist at the Institute for Advanced Study, has made a lot of progress applying geometric invariant theory and stability to understand a number of a general class of problems in computational complexity theory. And here's some recent papers on this, which I think might stimulate some sort of interesting contact between our considerations and this quite interesting branch of computer science. So let me stop there, and thanks again for your attention, and I'll ask for questions.
Cool. Thank you very much, Mike, for a really interesting talk. Let's thank Mike for his. Let's see, are there questions?
On your last slide, Mike, you say the first bullet on your last slide says talks about the quintic hypersurface. Do you mean kind of a general one, or a specific?
Well, yeah. let's see. I mean, you're talking about again, for everything we do, we do pick particular hypersurfaces with particular polynomials. I mean, when I say I mean, do you have a more specific question, or? I mean, so for example, these basic graphs of results. What have we done? We've scanned through a set of so we've taken these two-dimensional families, right? Like this F2 here is a two-dimensional family with parameters psi and alpha, and now we just scan through some list of psis and alphas, and rather than plot the dependence on psi and alpha separately, what we do is we work out this proxy of distance to the discriminant locus function of psi and alpha, and then that's the x-axis of the graph I'm giving here, and then the y-axis is this log of the error. So I've taken a list of maybe 100 different points in moduli space, 100 different Calabi-Yaus, and summarized them in this graph.
Right. Thank you. Yeah.
Other questions?
Yeah, Mike.
Yeah.
Great talk. Thank you very much. I was wondering, how well do the networks behave when you look at large complex structure limits? Can you take sites that are very large, for example?
Yeah. We didn't have time. That's an interesting question. We didn't have time to do justice to that. That would be worth following up.
Thanks.
Could I ask a question about the Hermitian-Young-Mills implementation? So is the setup of the networks that you're doing at the moment that you have to compute the Calabi-Yau metrics first and then compute the connection, or is there?
Yeah, that's what I'm doing. You would first do the metric, and that's right. And in particular, what I'm saying here is that you wouldn't even, you would want more than the metric. You would probably want to have these intermediate layer outputs available.
This is not something I've thought about at all, but do you have any ideas of, I mean, would there be any way to sort of streamline that as like one network to do both? Or, I mean, I don't know.
Yeah, well, I mean, from a technical point of view, you're probably better off not doing that, but having, I mean, from a technical point of view, you would program it as one network, but you probably would first train the metric network and then just load in those coefficients and not continue to train them, but, I mean, you could, of course. I mean, we haven't tried to program this yet, but this is not going to be any harder in TensorFlow than the rest.
I guess the nature of my question was, this is a bit amorphous, but it wasn't so much a question of network architecture as more, is there sort of any in principle way of trying to phrase the entire problem as like a metric on the total space of the bundle? But this is not known to me if this exists. But.
Yeah, I don't know one either. I mean that would be interesting to think about.
Thanks.
So I had a question about this second minimum. I missed what was the meaning of this second minimum? Was this something just to do with?
Yeah. Sure. Just a sec. Let me put it up here. Okay. So what this is to say we'd like to know for a given point in moduli space what is basically the maximum curvature of its Ricci-flat metric. Okay, and we'd like to. Again, we like some much simpler calculation that estimates that. And so if you're close to the discriminant locus, then a reasonable measure of that is distance to the discriminant locus. And the correct measure would be some sort of distance in the Weil-Petersson metric, which is very hard to calculate. But as you get close to the discriminant locus, there's this pretty accurate proxy for it, which is this kind of distance of, it's even simpler, you can show its equivalent. It's basically the minimum value of the norm of the gradient of the defining polynomial. And so then that's what I've plotted. And so then, of course, for the one parameter family, you could compute that, and you've got this Riemann sphere with three singularities, and that it's plausible. I haven't checked it, but it's plausible that as you get up to the equator, then you're closer to the conical singularity because you can go around the equator. It's like more like an elongated, cigar type of sphere. And then this work of Cui and Gray had studied exactly this dependence on distance to discriminant locus, and they had found this interesting behavior where the error gets worse as you pass through that region on the opposite side from the conical point. And so now I've just calculated that proxy, that norm of the gradient for the as a function of the moduli, and indeed you do see this dip at the other side from the conical point.
Thank you.
Interesting.
I'm wondering if your method with these subspaces of sections could be related to embedding in weighted projective spaces, where you could.
Maybe. I'd be very interested to, again, the basic definitions are quite simple, and so I'd be very interested if there's other geometric interpretations. One connection. Again, this is, obviously the people that work in machine learning think very differently than us, and not so geometrically. But one connection to more, sort of traditional mathematics, which people have tried, is to dynamical systems theory, to say that obviously you can think of the layer as like a map, and you can ask about fixed points of that map and so forth. So people have, for example, the statements about approximation theory to show that such and such function can be well approximated with 4 layers and not with 3 layers. Sometimes you can use dynamical systems arguments. Mm-hmm. But what you say sounds interesting. I would like to hear more.
Thank you.
Mike, have you managed to think? Have you got some ideas about how one could apply some of these ideas, or develop some of these ideas for the non-supersymmetric Ricci-flat problems?
Well, I haven't. I would certainly like to, and then perhaps we can discuss that. The kind of. I think this will be a very fruitful topic to discuss tomorrow. I don't have such coherent thoughts to give you an answer, but I have lots of ideas.
Mm-hmm. That'll be good to discuss that tomorrow, definitely.
Yeah.
Even other exceptional holonomy as an intermediate.
Yeah, also.
Yeah, I think quite a bit on the computational level. I think I wouldn't say we solved all problems, but I would say that there's a lot of power there just using existing software, and the issues will be more mathematical ones of representing metrics that involve many functions to describe the metric, and finding either good coordinate system that doesn't become singular, things like that. That definitely, we could discuss and perhaps find good approaches.
From the physics point of view, what would be the most important things to compute? If you could.
Well, of course, the one which was the most studied were these Yukawa couplings and the heterotic string, which someday I think will be the most important. Now, from where we stand now, I don't know. There's certainly these questions about flux vacua that have become very controversial, and so that's an area where one could do more numerical things, and so that's not a pure metric problem, of course, but it's sort of like these how to say, there's like this whole Strominger system, and then things that look kind of like that, where you postulate some integral form, so some P form, you have the metric, you have some auxiliary scalar function, and you've got like 2 or 3 or 4, equations that govern them. And then the question just would be, we don't know that solutions always exist. Do solutions, we have cases where solution clearly exists in some sort of expansion around the large volume, and then as you make the volume smaller, does the solution keep existing, or does it break down someplace? So that would be a very valuable, I think, kind of question to be able to analyze. Maybe again for discussion tomorrow. Yeah.
And I have another quick question, Mike. So you talked about you use this reduced parameter space that you get from the neural network with this log growth as opposed to the polynomial growth in the number of parameters.
Right.
And you seemed a little worried about whether or not you can actually approximate the functions that appear using this reduced parameter space, right?
Right.
Do you actually run into this problem on any, say, Calabi-Yau threefold, or because if I thought I was going to run into this problem, I would have thought I'd run into it on a non-symmetric quintic, for example, right? But it seems like your networks do just fine.
Well, we have to be more quantitative. I mean, if 1% is fine, then we did that. But again, those plots that I put out do show the limits of ability to approximate. And so like here are examples where in this one, the green, okay, so the pink is like the best you could do at k = 8. The green is a neural network that's got really almost as many parameters, and it is doing just as well. And this kind of purplish dot is a network that has 20 times fewer, 10,000 parameters instead of 200,000. In this regime, it just doesn't do as well. And we got enough data to be pretty convinced of that. And so I think I think this contradicts the claim that it's just the depth of the network, is the only important thing. And I think the number of parameters does play a role. And so then I tried to formulate some sort of theoretical simplification of that question. That's where this polynomial logarithmic kind of distinction came out. But maybe again, there are a variety of questions one could formulate that way. But these questions that involve either how big is the function space, how many parameters and so forth. They are also interesting questions.
Great, thanks.
So just following up on something you mentioned just in your previous answer about these whole Strominger type systems.
Yeah.
So I was looking at this system in dimension 7, but I'm sure the same sort of things happen in dimension 6.
Yeah.
You can find solutions which are arbitrarily good. There are solutions up to arbitrary high order and alpha prime, but I suspect that there are no genuine solutions. I mean, is this an issue, or is this something that?
Oh yeah, of course. Well, I know in general that's an issue. Can you tell me why that would be the case here? Or?
I think what happens is that you can. It's a case where the manifold is an S1 bundle over something, and you can make that circle really, really small, and so you can't tell the difference between the kind of the model that's happening on the base and the thing lifted up to the total space. So you can make the sort of errors that come from the fact that your S1 bundle is non-trivial. You can make those as small as you like, and so you can make it a solution up to arbitrary high level in alpha prime. But I suspect there is no solution unless the bundle is.
So your actual ansatz isn't really general enough, but you don't see it in any finite order.
No, that's right. So it's sort of saying in some kind of adiabatic limit or something.
Yeah.
There's a solution, but there's no genuine solution.
Yeah. Well, I mean, I'm not knowing any of the details. Of course, one would be tempted to say, well, okay, there's a problem where you just need a better ansatz.
Sure. Yeah. But I was just thinking on the numerical level, you probably couldn't tell the difference between.
Yeah, that's right. There's always that. You have to be careful of what kind of. What conclusions you draw numerically. Although again, this would certainly not show up in quite the same way because it wouldn't be a series expansion, So if you have some sort of uniform control of the error, you still might see that the error is not vanishing someplace.
Okay, thanks.
Yeah.
Are there other questions? If not, let's thank Mike again.
Yeah, thank you.
And